explore Newton's second law further. Just rearrange it a little bit to see how that works out. And the first thing we were going to want to do, remember, force is indeed a vector, and that is equal to m, which is a scalar, times the acceleration, which again is a vector. Yes, there we go. And if we rearrange things slightly, we recall that acceleration is equal to, if acceleration is equal to the change, that's right, where are we, delta, the change in the velocity, which is a vector, okay, like so. So if acceleration is equal to the change in the velocity vector over change in time, we can rewrite this as m times this, and here I'm just going to copy and paste the force in there. So I'm going to rewrite it like this, and let's absorb, if you will, the m into the v, because if we recall, momentum p is equal to mv, correct? And so the differential, or the change in momentum, then that is equal to m dv, or delta v, because m is a scalar, so m doesn't change usually. And in some cases, we'll figure out that the velocity is constant, but the change in mass is actually more apparent than the change in velocity. So in some other cases, we can flip-flop it. But in this case, we want to consider mass to be constant and velocity to be the change. So we will finally, or thusly, write is equal to, or the force is equal to the change in momentum. I always forget, I need to plug it into this thing, that change in momentum over the change in time. This is another presentation of the second law of Newton. We can also represent it as a differential equation, which is kind of like, it's my favorite form of presenting it, because recall this item over here. We're just going to substitute, put m, that. Yes, we're just going to substitute that, and also recall if v equals the change, oh no, I need this, the change in position, over the change in time, we can write, nope, I don't know what I just did, oh yeah, if we can write v, or actually we know v is the change in position over the change in time, we can rewrite this as force is equal to m times the double derivative, or the double derivative of x over, with respect to time, sorry. I always forget that these need to go first. Where is our plus Lee, we can write that is equal to the force over the mass. Which is a little bit strayed from standard form, but we can actually work with this. We can take this a little step further into analysis. We can take a derivative. We can integrate. And how we're going to do that is by getting some mathematicians angry at us physicists and just take a dt and multiply it to the other side, so it'll look like this times, and if you know the reason why mathematicians get mad at this procedure, go ahead and write in the comments. I would like to know. All I know is that some of my friends always say, no, that's not the way you're supposed to do it, and then I'm always like, oh, well, that's how I did it in my physics courses, so, we're right, you're wrong, doesn't matter, it works, right? I don't know. Anyhow, so we get on the left side just a dx dt. Should this still be t squared? Nah, I don't know. Oh, yeah, just a dx. Oops, just a dx. I'm gonna start learning the abbreviations for these. I promise y'all that. And this should be that times t plus our constant of integration, because again we are doing an indefinite integral, so that requires a constant, and I'm going to call it just v naught, and we're going to do the same procedure one more time and multiply by both sides by dt, and get some mathematicians angry with us physicists all over again, and plug this in over here. And this time I'll do y'all the favor just so I don't get any confusion. dt like that. So this probably looks better than my previous integral, but I'll excuse the crudeness. And anyway, then we get x is equal to this times t squared. And if y'all remember correctly, you're supposed to put it 1/2 here, just simple mathematical rules, because of the differentiation. I don't know, y'all should know that. And I really do not know how to explain it while typing at the same time. And here's our constant of integration, x naught. So v naught and x naught are our initial conditions of the problem. So then it just varies where your object starts and if it has an initial velocity. But this is again taken just simply from the second law of motion. Kind of an interesting, I don't know, side product, and I'm gonna just simplify this and take off the vector, make this a scalar, since I totally forgot about the x being a vector. So at this point we'll deal with magnitudes, make this a whole simple linear problem.